When studying special relativity, there are probably some things that don't make common sense to you, and I have created this video to help solve those problems. The paper for this video is available at the following site. First, I would like to briefly explain special relativity and the contents of this paper. Dr. Einstein, thank you for coming from so far away.
Nice to meet you. In special relativity, there is no stationary inertial frame.
Can't we just say,
there is no way to measure the velocity of a moving inertial frame.
I think we can get it by experiment like this.
If you look at the light in front of you from a spaceship traveling at the speed of light, it appears to be at the speed of light.
I see it at 0.5 c.
The mass of a moving object increases like this.
I agree. The mass of a moving object increases. However, I think it depends a bit on the direction. In my paper, I used a unique method to derive the mass increase.
I expressed momentum simply as mass times velocity, but your equation is a bit more complicated.
Yes, my equation is a bit complicated, but if you substitute 0 for v0, it's exactly the same as yours.
I derived the object's kinetic energy equation like this.
I derived it like this.
I didn't know the Haffel-Keating experiment, which was conducted when I wasn't in the world.
I can explain why the westward flight time was faster than the time at the airport. The calculations based on my theory agree to some extent with the Haffel-Keating experiment results.
I see. I'm busy. I'm going home to complete the unified field theory that I couldn't finish in my lifetime. Have a nice day.
Thank you for coming from so far away. Goodbye. Based on this motion of light, Einstein derived the equation for kinetic energy like this. If the actual movement of light is like this, how can we derive the kinetic energy equation? First, I will explain the contradiction in special relativity that I think, and the ideas, and 3 new assumptions to resolve the contradiction. Then, I derive new equations for kinetic energy, momentum, and inertial mass. Finally, using the theories in this video, the speed of light seen from a spaceship flying at near the speed of light, the Haffel-Keating experiment, and the twin paradoxes are analyzed. As shown in the figure above, let's assume that when observing a spaceship from the Earth, 30 seconds pass on the Earth's clock, and 15 seconds pass on the moving spaceship's clock. However, according to special relativity, all motion is relative, so when observing from a spaceship, the Earth is moving, so the Earth's clock should go 15 seconds. Then, to find out which clock was really slow, we can compare the 2 clocks when the spaceship returns to Earth. In special relativity, when light is emitted from the center of a moving train, observer A on the train observes that the light arrives at the front and back of the train simultaneously. When observer B on Earth sees this light, he observes that the light arrives first at the back, and later at the front. This is the relativity of simultaneity. However, if we put precise clocks at the front and back of the train to record when the light arrived, wouldn't we know which light came first? As seen from Earth, spaceship A and B fly to the right for 1 second at 0.7 c and 0.9 c respectively, and spaceship C flies to the left for 1 second at 0.9 c. The velocity of spaceship B observed by spaceship A is calculated in special relativity as follows. This velocity is obtained by dividing the Lorentz distance by the Lorentz time. In the same way, we can find the velocity of spaceship C observed by spaceship A. But isn't it strange that on spaceship A, different times are used to find the velocity of spaceship B and C that have moved away in the same amount of time? Isn't it correct to calculate the relative velocity of spaceship C and B as seen from spaceship A by dividing the distance of spaceship C and B from spaceship A by the same amount of time observed in spaceship A? One late winter night, while walking with Dubu, I saw 2 stars. It suddenly occurred to me that what if the speed of light from those stars was the same regardless of the speed of the stars, and that the speed of light is only the same in a stationary inertial frame? Imagine you're in a spaceship flying through space. A light bulb and a reflector mirror are inside a spaceship. When the light bulb is turned on, special relativity states that the speed of light is constant in all inertial frames, so we expect the motion of light to be like this. However, based on my ideas of light from the walk, and the results of the Michelson-Morley experiment, I imagine the motion of light as follows, where the round-trip speed of light is the same for all directions. So, I made 3 assumptions. First, a stationary inertial frame exists. Second, the speed of light is only the same in a stationary inertial frame. Third, the round-trip speed of light in a moving inertial frame is the same in all directions, and is equal to the speed of light in a stationary inertial frame. As shown in the figure above, to calculate the kinetic energy of a golf ball hit by a rabbit in an inertial frame moving at velocity v0 in a stationary inertial frame. Derived 4 conversion factors for length, time, velocity, and mass. Imagine a spaceship flying at velocity v0, and you are outside the spaceship seeing the light emitted inside the spaceship. Looking at the light inside the spaceship from a stationary inertial frame, the light path to the reflector for theta would look like this. The light is then reflected, and returns to the origin like this. On this path, the relationship between time t1, t2, and distance L is as follows. The path of light to the ceiling in the spaceship will look like this. And the light returns to the ship's origin like this. On this path, the relationship between times t3, t4, and distance L0 is as follows. Based on assumption 3 that the round-trip speed of light is the same, t1 plus t2, and t3 plus t4 should be the same. Therefore, the relationship between L0 and L, i.e., the length conversion factor, can be obtained like this. The meaning of this equation is that the length L0 of a spaceship flying at velocity v0 appears to be contracted to L in a stationary inertial frame. If we define a unit time in an inertial frame as the time it takes for light to travel a distance L0 back and forth, then the unit time in the inertial frame will look like this. However, if you look at the unit time of the moving inertial frame in a stationary inertial frame, the unit time of the moving inertial frame will appear to go slower as shown. In a stationary inertial frame, the unit time t0 is given like this, and the moving inertial frame unit time t is calculated like this. Based on this relationship between t and t0, the time conversion factor RT can be obtained like this. If a stationary inertial frame exists, how can we find out the proper velocity v0 of a moving inertial frame relative to the stationary inertial frame? In a moving inertial frame, the path of light to a reflector, and back to the origin is as follows, and the times t1 and t2 can be represented like this. Therefore, the time difference between the time t1 when the light arrives at the reflector, and the time t2 when it returns to the origin, can be expressed like this. If we convert this time to the time in a moving inertial frame, it can be expressed like this. In this equation, the maximum time difference occurs at theta 0, so we can represent the maximum time difference, and v0 like this. If we can find the direction in which the maximum time difference occurs in an experiment, we can find out in which direction and at what speed the Earth is flying through space. Using the length conversion factor and time conversion factor obtained before, we can find the factor that converts the velocity in the moving inertial frame to the velocity in the stationary inertial frame like this. In special relativity, the mass increase was deduced as follows, but not perfectly derived. Transer Z and Astroboy promised to shoot a 1 kg ball vertically at 10 meters per second on Earth, and in a spaceship flying at 0.4359 c. When Transer Z looks at Astroboy's ball, it was only 9 meters per second, so he asked Astroboy why you shot the ball at 9 meters per second, but Astroboy says, I definitely shot the ball at 10 meters per second. Believing Astroboy, Transer Z thinks that due to the time dilation, the mass of Astroboy's ball has increased like this to conserve momentum. However, if Astroboy shot a ball at 10 meters per second in a horizontal direction, due to the time dilation and length contraction, Transer Z will see Astroboy's ball at a speed of 8.1 meters per second. Then, in order to conserve momentum, Transer Z thinks that Astroboy's ball has increased like this. As you can see, the mass increase is difficult to explain completely in special relativity. I used the following 2 approaches to derive the mass increase. Consider a bomb of mass m0 flying at velocity v0, and exploding at velocity v1. Approach 1. the mass increase is assumed to be as follows, and the mass of the bomb flying at velocity v0 is assumed to be proportional to the mass increase, so the explosion energy is assumed like this. The kinetic energy of a fragment in a stationary inertial frame can be integrated from 0 to RV(v1), taking into account the velocity conversion factor. For n0.5, the total explosion energy can be obtained by integrating the fragment kinetic energy over all directions. Since the explosion energy for n0.5 is the same as the explosion energy assumed above, we can deduce the mass increase like this. I honestly don't like the first approach. This is because we assume and derive the mass increase. In the second approach, I try to derive it without assuming the mass increase. If the explosion velocity v1 is very small compared to the speed of light, the kinetic energy of the fragment can be approximated as follows. Where gamma0 is the mass increase due to v0 before the explosion, and gamma1 is the mass increase due to the average velocity of the fragments after the explosion. The total explosive energy of the bomb can be obtained by integrating this fragment kinetic energy over all directions. Assuming the explosive energy of the bomb like this, then we can solve these two equations to get gamma0 gamma1, which is the ratio of the mass increase before and after the explosion. Based on this equation, we can assume the mass increase like this, and directly substitute v0 and the average velocity of the fragments into this mass increase. Then, we can get the same ratio of gamma0 and gamma1 as above. Therefore, we can deduce the mass increase like this. An object of mass m0 is thrown at velocity v1 from an inertial frame moving at velocity v0. The velocity and mass of the object seen in a stationary system are as follows, and the velocity and mass of the moving inertial frame are as follows. We can calculate the kinetic energy observed in the stationary inertial frame by integrating the kinetic energy of the thrown object and the moving inertial frame like this. According to the law of conservation of energy, the kinetic energy calculated in a stationary inertial frame, and the kinetic energy calculated in a moving inertial frame, must be the same. By differentiating the energy equation derived in a stationary inertial frame, we can obtain the instantaneous momentum in a moving inertial frame like this. The momentum of a moving inertial frame can be calculated by integrating this instantaneous momentum like this. As we derived, mass is a function of velocity. So, how can we express the rest mass in a moving inertial system? Momentum is defined as mass times velocity. So, if we divide the momentum when v1 is almost 0 by v1, we can get the rest mass like this. As shown in the figure below, the rest mass in a moving inertial frame is a function of velocity and direction. So far, we have been deriving equations in two-dimensional coordinates. Let's try to derive equations in three-dimensional coordinates based on the figure below. First, the length conversion factor is. The time conversion factor is the same. The velocity conversion factor is. Based on the figure below, the kinetic energy in three-dimensional coordinates was derived like this. The momentum is like this, and the inertial mass is like this. Using the equations derived in this study, I solved the following problems. In a spaceship traveling at near the speed of light, Einstein saw the speed of light ahead of him as c, but I saw light at 0.5 c. Who's right? If an object is thrown at velocity v1 in an inertial frame moving at velocity v0, the object's velocity in a stationary inertial frame will appear to be velocity va like this. Since the velocity va observed in a stationary inertial frame cannot exceed the speed of light, the maximum velocity of v1 made or observed in a moving inertial frame can be calculated by substituting c for va, and solving the above equation. The three-dimensional equation for the maximum velocity in an inertial frame moving is like this. In this equation, if the speed of the spacecraft, v0, converges to c, then the velocity v1 for the front light converges to 0.5 c. Numerically solving this equation, all light ahead of a spaceship near the speed of light converges to 0.5 c, as shown in the figure above. The maximum velocity that can be observed or made in a moving inertial frame varies in different directions as shown below. So I calculated the average of this maximum speed. To calculate the average of the maximum speed, imagine traveling around a circle of radius d at maximum speed in each direction. The time it takes to go around the circle is the 360-degree integral of the time for each segment. Then divide the circumference of the circle by this time to get the average speed, which is always c, regardless of direction. Maybe this explains why particle accelerators cannot produce particles faster than the speed of light. The Haffel-Keating experiment was conducted in 1971 to prove special relativity. An atomic clock was placed at an airport, and circled the Earth in the east and west directions. It was an experiment to confirm the time dilation expected in special relativity by comparing the atomic clocks at the airport, and the atomic clocks in the two airplanes. Before the experiment, the time dilation due to general relativity and special relativity was predicted like this, and the experimental results were like this. In this experiment, if the predicted time dilation by general relativity is correct, then the time dilation by special relativity is. According to special relativity, all motion is relative, so whether the airplanes are traveling east or west from the airport, they are both relatively far away from the airport. So an observer in the airport expects that the time of both airplanes is going slowly. However, experiments have shown that only the time of the eastern plane passed slowly. Using the theory of this paper, the Haffel-Keating experiment is interpreted. Let's imagine an airplane circling the Earth from an airport in the east and west directions under the following conditions. If you look at these two planes from outside the Earth, it would appear that the plane that flew eastward circled the Earth twice before coming back to the airport, and the plane that went westward would come back to the airport before circling the Earth. The angles the two planes traveled, and the angle the airport moved can be obtained like this. In the figure above, the inner red circle represents the Earth's rotation, and the outer blue circle represents the path of the airplane. The time it takes for the Earth to rotate d theta at the center of the Earth, i.e., without rotation, can be represented like this. Converting this time to the time in a stationary inertial frame, it is like this. The time at the Earth's surface, given the Earth's velocity v0 and rotation, can be represented like this. Similarly, the time it takes for an airplane to fly d theta can be calculated like this. Based on the solar system's rotation around the Milky Way at 230 km per second, assume v0 is roughly 300 km per second. The time on the plane flying east, and the time at the airport are calculated like this, and the time on the plane is calculated to be 239 nanoseconds slower than the time at the airport, which agrees to some extent with the experiment result. The time on the plane traveling west, and the time at the airport are also calculated like this. The time on the plane goes 174 nanoseconds faster than the time at the airport. This calculation agrees to some extent with the experiment result. Let's say, the older twin is traveling to an orange star in a spaceship, and the younger twin is on Earth. Let's express the time that has passed for the younger twin on Earth until the older twin returns from space like this. Converting this time to time in a stationary inertial frame is like this. The time that has passed for the older twin in the spaceship to reach the orange star is. When the spaceship returns to Earth, it will come in the opposite direction, so v1 will be negative, and the time elapsed in the spaceship will be like this. Therefore, the time that has passed for the older twin during the round trip would be. For example, if a twin brother travels in a 0.7c spaceship to a star 7 light-years away, 20 years pass for the younger twin on Earth, and 14 years pass for the older twin in the spaceship. Finally, let me tell you about the experiment I talked about in this video. I don't know if it's technically possible to measure the speed of light in a one-way direction rather than a round trip. However, if successful, the experiment will be a milestone in the history of physics, as it will tell us where and how fast the Earth is flying in space, and by extension, where the solar system came from. This movement of light that we believe we have measured. Maybe it looks like this. I think the challenge for 1% success is much more meaningful than giving up without a challenge. I look forward to your challenge. Thanks for watching.